So for learning target 4.4, which is still solving a system of equations, but we're using something called the elimination method, which says to make it so one variable in the equation is the same, but the number is opposite signs. So like 4x and negative 4x. The reason that you're doing that is because you want to be able to add these two equations together and eliminate or get rid of one of your variables. And if I add opposites, 4x and negative 4x, I get 0, and so that would eliminate the x term. Now, it may already be true. You may have to multiply one equation by something to create opposites, or you may have to multiply both equations by something to create opposites. We're going to add the two equations together once we get one of our sets of variables to have opposite coefficients, and then solve for the variable that's left. And then just as we did in the substitution method, we'll solve the value of the variable that we just found back into one of the equations to find the second variable. When I look at these two equations, I'm checking my x terms, and if I added x and x together, I'd get 2x, so I wouldn't eliminate my x's. But if I look at the y terms, if I add a positive 7y to a negative 7y, it's 0, so I would be able to eliminate my y terms if I add these two equations together, which means I already have opposites. The positive 7 and negative 7 coefficients of y are opposites. So when I add these two equations together, a 1x plus another 1x is a 2x. Double checking, positive 7y minus 7y is 0, so I don't write plus 0y, it's just 0, so I don't need to write it. And then I have a positive 13 and a positive 5. Again, I'm adding these equations together, and that would give me a positive 18. Solve by dividing both sides by 2 to get x equals 9. Now, I know that the point of intersection, if I graph these two lines, is 9 something. I need to find the something. So I'm going to take the 9 that I just found for x and substitute it for either one of these x's. It doesn't matter which one. I'm just going to go with the first equation. So I had x plus 7y equals 13. I know now that x is 9, so this becomes 9 plus 7y equals 13. I'm going to subtract 9 to move that constant to the right and eliminate it from the left. I end up with positive 7y equals positive 4. Then when I divide both sides by 7, I get y equals 4/7. So I think that the answer is the point positive 9, positive 4/7. If I were to graph these two lines, that's the point of intersection. To check this, I'm going to go to my equation I didn't just use, put 9 in for x and 4/7 in for y, and check it by punching that in my calculator. 9 minus 7 times 4/7, it's not 7 and 4/7, it's 7 times 4/7, is 5. So that's true. That is the answer to my system of equations. Now, the coefficients of my p, 2 and 5, are not opposites. And the coefficients of my q, 3 and negative 1, are not opposites. I could say, well, 2 and 5 both go into 10, so I could multiply by something to give me a positive 10p and a negative 10p, and that would be okay. But I notice that 3 and 1 both go into 3. And this one's already positive 3, so I don't need to multiply that one by anything. And if that one's positive 3, to create opposites, I want this one to be negative 3. Since it's already negative 1, I'd have to multiply it by 3 to make this a negative or minus 3q. When I multiply by 3, notice the parentheses around the entire equation. Everything gets multiplied by 3. So 3 times 5p is 15p. 3 times a negative 1q is a negative 3q, so I write minus 3q. And then 3 times 11 is 33. Now, I'm just going to bring this first equation down and write it below the one I just rewrote so that my two equations that I'm going to combine are together. Makes it a lot easier to do. Let's see what's going on. 15p plus 2p is 17p. Again, I should be adding these equations together. Double checking, negative 3q plus positive 3q is 0, so I just eliminated my q terms. 33 plus 18 is 51. Solve then by dividing both sides by 17, and p equals positive 3. Even though I don't have x and y, inside the ordered pair, I'm going to do this in alphabetical order. P comes before q alphabetically, so the 3 comes first in my ordered pair. Now I know p is 3. Again, I can go back to either one of these equations and substitute 3 in place of the p and solve for the q. One doesn't look appreciably easier than the other one, so I'm going to go back to just using the first one. I know that p has a value of 3, so now it's 2 times 3 plus 3q equals 18. 2 times 3 is 6. Bring down my plus 3q equals my 18. Just going to solve this by subtracting 6 from both sides to eliminate the constant on the left and move it to be with the constant on the right. So I have a positive, because of the plus in front of it, 3q equals positive 12. Then when I divide both sides by 3, q equals 4. Now I can check that. I just used the first equation to get that variable, so I'm going to substitute 3 for the p here and 4 for the q. 5 times 3 is 15, minus 4 is 11. So it does check in both equations. Now this is the situation where 2 and 7 aren't opposites, and 2 won't go into 7 evenly. 3 and 4 aren't opposites, and 3 won't go into 4 evenly. So I either need to say 2 and 7 both go into 14 and multiply so that I have a positive 14x, negative 14x, or 4 and 3 both go into 12 and multiply so I have a positive 12y, negative 12y. In this case, because I'm going to have to multiply both equations by something to create opposites anyway, I often go to where the signs are different to begin with. One's already a plus and one's already a minus, because I need to have one coefficient be positive and one negative. So since 4 and 3 both go into 12, if I multiply the first equation by 3, this will make this a plus 12y. Multiply the second equation by 4, it'll make this one a minus 12y. Then I'll have opposites. Rewriting this first one, 3 times 2x is 6x. 3 times a positive 4y is a positive 12y. So I write it as plus 12y equals 3 times 40 is 120. Now the second equation, 4 times 7x is 28x. 4 times a negative 3y is a negative 12y, which I'll write as minus 12y. And 4 times 4 is 16. 6 and 28, both positives, gives me a positive 34x. Plus 12y minus 12y, that's 0, so my y term is eliminated. And 120 and 16, they're both positives, so I get 136. Divide both sides by 34 to isolate the x, and I get x equals 4. So my point of intersection is the point where x is 4. I just don't know why. Now, again, go back to one of my equations. I'm going to use the second equation because I've used the first one every time so far. And it shouldn't matter. If this is the right value of x, I should get the same value of y, no matter which of the equations I put it into. So x is 4. So 7 times 4 minus 3y equals 4. 7 times 4 is 28. Then minus my 3y is 4. Subtract my 28 to eliminate the constant on the left and move it to be with the constant on the right. Be careful when you bring this down. With the minus in front of the 3y, it comes as a negative 3y equals negative 24. And then divide by negative 3 to get y is positive 8. So it's the 0.48. Now it just happened that in these equations, we were quite often eliminating the second variable. You don't have to eliminate the second variable. Sometimes it's easier to eliminate the first variable. Just look and see which one's easier to eliminate and eliminate that one. So in the special cases, I don't have opposites already, but I notice if I multiply 5 by 2, I'd make this a positive 10x, which would be opposites with the negative 10x. So I'm going to multiply everything in the first equation by 2. 2 times 5x is 10x. 2 times 3y is going to make this a plus 6y. And 2 times 10 is 20. Now, when I add these equations together, negative 10x plus 10x is 0. Negative 6y plus 6y is 0. This side just becomes 0. And negative 12 plus 20 is 8. This is the situation where I've eliminated both of my variables, and I get a statement that is never going to be true. 0 is never going to equal 8, so this is no solution. If I actually graphed these two lines, they would be two different lines, but they would be parallel. No solutions means they never intersect. Again, I don't have opposites already, but if I multiply the first equation by 2, this would make this a minus 6x, which would be opposites with this plus 6x. So 2 times a negative 3x is a negative 6x. 2 times a positive 4y is a positive 8y. And 2 times negative 7 is negative 14. This is similar to the previous problem in that I end up with 0x and 0y, so this side is 0, but 14 plus a negative 14, or 14 minus 14, is also 0. So in this case, I've eliminated both variables, but I end up with a statement that is always true. 0 always equals itself. So this is the infinitely many solutions, and that's spelled infinitely. And if I were to graph these two lines, it turns out they're actually the same line. And you saw that when you did the graphing as well. So that is the elimination method. Please do the problem at the bottom of the page before you come to class.